Okay, welcome back. This is the first half of Chapter 8. Chapter 8 is on graph algorithms, page 231. And of course, we're not talking about, pie charts and things like you do in Microsoft Excel. Those are charts, but not from the mathematical perspective. From a mathematical perspective, we're talking about, a series of dots on a two-dimensional landscape with lines drawn between them, as an example. So a graph is a formal description of some very common problems that come up. For example, a road map. So a road map could be considered like a graph because there are intersections, which would be dots, and then lines that connect the dots together, those would be roads, right? Kind of simple. And so the intersection of two roads, or three or four, is a node, and the actual roads are called edges. That's kind of a weird term, but anyway, node and edge. And so there's some other kind of weird concepts. Just like in the real world, you could have a one-way street, and that would be called a directed graph, where you can only go down this particular street in one direction. Okay, that's pretty cool. And then there's another one called a weighted graph, and that is I have two roads that can take me to the same location, but one of them is a toll road and one of them is not. So one of them costs me, and so I have a decision to make. Do I take the cheaper route to get to my destination, or do I take the more expensive route? And so the toll road analogy is pretty good when it comes to describing a weighted graph, because not only do the edges have distances, the distance itself might not be the determining factor. It could be some other thing. So they attach a weight to each one of the edges to help you decide. Okay, so let's talk about some more analogies here. Let's say you're sitting in your car and you have one of those fancy, sat-nav setups, that uses GPS technology to route things. And so you're sitting at the parking lot of some liquor store and you're trying to find the nearest drugstore for your hangover medicine. And so you type in, drugstore, and it calculates the shortest distance from where you are to where you need to be. And that's pretty doggone cool. And that's going to be using a technique not in this half of Chapter 8, but in the next half of Chapter 8. But finding the shortest path is a pretty doggone cool trick. And we're going to be writing algorithms that do that. Yep. So if you went to Google Maps and you were trying to plan a trip, one of the things you could do in Google Maps is you could say, I want to avoid interstates because I don't like driving on the interstate. So it will route you around an interstate. Or you can say, I want the scenic route. Well, somebody's gone in and added weights to these things, where a scenic route has a higher weight than a non-scenic route, and then, a toll road or an interstate would have very low weights, or maybe the other way around, whatever. The point is that it can figure out how to route you to your destination using your preferences based upon these weights. So this is very common things. Now let me give you another example from the world of computers. So in the way the internet works is basically we're a bunch of connected routers, okay? So that's how the internet basically works. One router talks to another router. So this one router might talk to 5 routers. And then each one of these routers talks to 5 other routers to include themselves. So it's kind of a mesh, right? So this guy talks to this guy, plus this guy talks to that guy, and I can talk to that guy. So it's a complete mesh of all routers. And the idea is if one of the routers died, all the messages would be just routed around them, and no one would ever know that the router was down. That's the whole concept of this kind of a mesh network. But when it comes time for me to update my routing information, for example, I added an extra node over here that everyone in the cloud needs to know how to get to that node. And so I need to do a router update. And so you could just say, hey everybody, I added something, and it would just blast it out to everyone. But that's not very efficient. The more efficient way to do it is to I talk to all my nearest neighbors, and then all those guys talk to all their nearest neighbors, and that guy talks to all of his. It goes out in waves. I hit all my neighbors, poof, and then they hit all their neighbors, poof. Then they hit all their neighbors, poof. Now you might be able to see a problem there, because if you're highly integrated and got lots and lots of connections, you may be offering an update that I've already got. So you need a way to traverse, that's a cool term, traverse the entire system, but minimize or eliminate any duplicate nodes. Okay, now that is something cool. That's called traversal. All right. So, later on, we're going to be talking about how in the world you store this kind of information, this little map, with dots and lines connected to it. And so there's two ways you can do it. You can store it into a two-dimensional array, or you can store it as a linked list. Now, I prefer the two-dimensional array. It's not necessarily the most efficient from a space complexity point of view, but it just makes things easier. I mean, I can kind of eyeball it and go, yeah, okay, that looks pretty good. I can visualize it a lot better than visualizing the linked list thing. Okay, moving on. So graph background and terminology on page 234. I gave you some of the terms. Gave you node and edge and traversal and weighted and directed, right? Okay. So let's keep going. So from a math perspective, a graph is an ordered pair of two sets representing nodes and edges. So you have a set of nodes and a set of edges. That's it. That's what the mathematical definition of a graph is. Okay. So often the problem is solved, whatever problem you're talking about, by traveling along an edge to get from node A to node B. Right? That kind of makes sense? So whatever it is you're trying to do, you're trying to talk to everyone. That would be one solution. You're trying to get to the point A to point B in the shortest method. That would be another type of a problem. So traveling from node to node is very, very common. Now, if you can get to the node without any other nodes in between, right, like the nearest neighbor analogy I just talked about, that's what's called an adjacent node. So A is adjacent to B, C, and D, but not E. E is way over here. So to get to E, I have to go through B to get there. Okay, so the nearest neighbor approach is the adjacent. So node A is adjacent to B, C, and D. Cool. All right. That's another cool term. Directed, one more time. Directed means, okay, I can get there, but I can only go down that road one way. So when I say I want to go from A to B, that means A to B only. I cannot turn right around. So when you're talking about a directed graph, you need to have a source and destination. If you're just talking which ones are adjacent, it doesn't matter if I say A is close to B and B is close to A. Those are the same, right? So when you're talking adjacency, it doesn't matter what order. But when you're talking directed, I need to maintain the order if there's a one-way street, so to speak. Okay, so here's some goofy diagrams of what we're talking about. So here we go. So this one talks about lines and edges, and and the circles are the nodes, and so a normal type of graph, and then a directed graph, which means this is a two-way street. This is a two-way street, but these guys are one-ways. Okay, so if I want to go from 1 to 4, if I want to go from 1 to 4, well, it looks like I could do it multiple ways. I could go from 1 to 2 to 4, or I could do to 1 to 3 to 5 to 6, or I could go 1, 2, 3, 5, 4, right? I have lots of choices. But when I come over here and I want to go to 4, there are not a lot of choices. I mean, I cannot go here. And, well, yeah, sorry. I can go here 1 to 3, but I can't go directly to 4. So I have to go 1, 2, whoa. That's not going to work because I can't get out of 2. So I have to go 1, 3, 2. Wait a minute, there's no way there. So this particular directed graph is a kind of a weird one in that I don't have any ways to get from 1 to 4. So there's a technique, a term it's called a complete graph. A complete graph is all nodes are directly connected. In other words, I can get to everybody. Okay? A path. A path is just like I described. A path is a series of edges. Now, to tell you the truth, since I don't have a name for this edge, when I said go from 1 to 3 to 5 to 4, I rattled off nodes, didn't I? But I'm really talking about edges, aren't I? And so a path is a sequence of edges that have to be traversed consecutively to be able to get there. And in theory, your goal is to not pass through something twice, because that would create a loop, or the possibility of a loop. And so just kind of keep that in mind. So when you tell a series of edges, I don't want to go from 1 to 2 to 3 to 2, because that could make things like spin in a loop. Now, when I say traverse a path from 1 to 4, am I assuming that we're talking about the shortest distance between those 2 points? No, not yet. Later, but not now. So when I say traverse or path, I'm not necessarily talking about the shortest distance. We're talking about a distance. For example, in this case, I can get there in multiple ways. I can do 1, 2, 4, and 1, 2, 3, 5, all the rest of those things. Okay. A cycle is those things where I could end up in the same spot. Like here, I could go 2, 1, 3, 2. And then 2, 1, 3, 2, 2, 1, 3, 2, over and over and over and over and over, right? So, yeah, that would be a cycle. Okay, so loops means I start and stop at the same node, some sort of a cycle. Weighted, of course, is one where each one of the edges has an artificial cost associated with it. And obviously, I don't mean money. In fact, the cost is typically a unitless number. So the cost of this road is 5, and the cost of this edge is 10. What does that mean? It doesn't matter what it means. All it means is this one is twice as costly as the other. That's what it means. So units are not really relevant. You could do percents. You could do 1 to 100. Pick whatever scale you want. It doesn't matter what the numbers are. So the weights are just one thing is more costly than the other. Now in the internet world, the cost is typically associated with the speed of the connection and the saturation. Right? If I had if I had 3 ways to get from point A to point B, I want to find one that has the highest speed connection, not some wimpy low speed thing, and I want to find one that's not 100% saturated. So there, the cost is speed and the speed and the congestion. Well, you could say the same thing with roads. You could say the speed limit, 75 miles an hour, and I'm not going through some construction site in Waco, and therefore I'm having an awful lot of congestion, right? So it's the same kind of concept. Okay. So continuing on, the cost is the sum of all of the weights in a path. So if I'm trying to get from here to here, I just add up all of the costs. And so that's how you come up with the cost of the traversal. Connected. Connected means there is a way that I can get to every single node from some starting location. Okay, so if I started at 1 over here, could I get to absolutely every single node? No. But what if I started at 4? If I start at 4, can I get to every single node? Yeah, it looks like I can. I can go here and there, and then I can make this little loop. Cool. Okay, so kind of sort of making sense. Connected means there's at least one path, but not necessarily where you started from, because that could be something a little slightly different. Okay, we're coming up on the 15-minute mark. We're going to go through a couple more terms, and then we're going to get in some cool little demos.